when it comes to device virtualization, the top-of-mind, undisputable framework to use is, of course, QEMU. In recent years, with the advent of low-latency I/O devices, there has been a growth in the use of technologies like vhost, which allows devices to be virtualized from a single process in the hypervisor. This is critical for efficiency because polling can be done from few cores to many VMs. However, vhost is practically limited to virt.io, so a new kind of technology is needed for other types of devices. I'm Thanos, and along with my colleague Swapnil, we'll present the MUSER framework, which allows us to virtualize devices outside QEMU. So as we said, if we want to use polling to achieve high performance, we can either use vhost and virt.io, which doesn't suit all types of devices, or burn an entire core per VM just for polling, because a VM's virtual device can only be emulated by its own QEMU process. As the number of VMs increases, this just doesn't scale. Also, if emulation for a particular device fails in QEMU because of a bug, then there's nothing we can do to fix it. The VM's gone bust. And finally, it is impossible to upgrade emulation for a particular device in a guest without effectively restarting the entire QEMU process, for instance, by live migrating the guest. And this can be a very risky procedure. One way to solve these problems is to move device emulation into a vfio mdev driver in the kernel. However, moving device emulation in the kernel has drawbacks. It's harder to write kernel code, it's harder to maintain it, and bugs can be much more disastrous than in user space. So the question is there a better way to solve these problems? Let's look at the complete picture. vfio mdev allows us to virtualize a device in the kernel, and by virtualize we mean either provide SRIOV capabilities for a physical device that does not support SRIOV, or emulate a device from a single context, which allows for efficient polling. However, as we said, moving device emulation in the kernel has its drawbacks. Now, QEMU allows us to emulate a device in user space. But unless we use vhost user and virt.io, we cannot emulate multiple devices from a single process in the hypervisor, and this makes polling prohibitively expensive. So what we came up with is combining the advantages of vfio mdev and QEMU without the disadvantages. And we achieve this by creating a framework that allows us to move device emulation in user space outside QEMU without using vhost user. We call this framework MUSER, which stands for Mediated User Space Device. In its core, it's essentially a vfio kernel driver that simply relays operations into a user space process. MUSER is not specific to QEMU, much like vfio mdev, but QEMU is our main use case. Now, Swapnil will explain how MUSER works under the hood.
Okay. So before going into the implementation details of MUSER, let us first have a look into the building components for MUSER, vfio, which stands for Virtual Function I/O. vfio is device and IO-MMU agnostic driver framework, which is used to access physical device directly from user space. vfio exposes physical device to user space in secure IO-MMU enabled environment. QEMU uses vfio to expose physical device to virtual machine. One physical device can be passed through to one virtual machine. Physical devices which supports SRIOV can be passed through multiple virtual machines. SRIOV implements the logic to implement multiple instances of the physical devices, and that can be passed through multiple virtual machines. But it is limited to the number of virtual functions implemented by SRIOV. So what about the devices which does not support SRIOV? vfio mdev framework can be used by such devices, and then those devices can also be passed to multiple virtual machines. MUSER leverages vfio mdev framework. So quick takeaways. Single QEMU process cannot emulate device for multiple virtual machines. A single physical device cannot be passed through to multiple virtual machines unless it supports SRIOV. vfio mdev framework can be used by physical devices and then that can be passed through to multiple virtual machines, but it requires implementation of vendor-specific mediated kernel driver. vfio mdev mediated driver implements the logic to share the physical device between multiple virtual machines, but it is not necessary that this mediated driver should be backed by a real physical device. It can also be a virtual device, and there comes MUSER. MUSER builds on top of vfio mdev framework and extends it to write virtual devices into user space. So what is MUSER? MUSER is framework for implementing PCI device emulation in user space. MUSER mainly consists of two components. One is muser.ko, which is a kernel implemented mediated device driver. And second is libmuser, which is a user space library. So what does MUSER offer? Single process can emulate multiple devices. This means from single process, application can poll for multiple virtual machines to get the I/O request, and on the other side, the same application can also poll to the physical device to get the I/O completions. This means that by doing this, we can save a significant amount of CPU cycles. Another benefit of using MUSER is it completely hides vfio and PCI specification related implementation, so it is hidden from the device emulation application. So device emulation application just need to link to libmuser and need to specify some device-specific data, which is device ID, vendor ID, PCI region supported, interrupts, PCI capabilities. And the device emulation also need to provide some callbacks for the PCI, for the commands, and those callbacks will be called by libmuser. So these callbacks are like handling PCI regions, capabilities, mmap, or device reset. So let us have a detailed look into the components of MUSER. muser.ko, which implements the mediated kernel driver. So it registers with vfio mdev framework and also provides the callback, which will be callback from vfio mdev framework, depending upon the commands coming from the QEMU side. On the other side, muser.ko also creates a character device to pass those operations to libmuser. So the communication between muser.ko and libmuser happens via this muser character device. So device emulation, which is libmuser, it opens the muser character device, and then it passes the device emulation information to muser.ko. Then it waits for command to be received from muser.ko. Currently, this wait is synchronous. We want to make it asynchronous by making it pollable, but that's one of the items for future work. The interface between muser.ko and libmuser is custom IOCTL. So now let us have a look into a generic command workflow in muser. So QEMU calls into vfio mdev and passes some command. Then this command is passed further down to muser.ko. Then muser.ko passes this command to libmuser, and depending upon the command type, libmuser calls into device emulation, and then device emulation can implement its own logic there. So in order to emulate a device, some main functionality needs to be supported. These functionalities are like DMA, mapping device memory, and interrupts. So now we will have a look into detail how muser handles all these main functionalities. So let's see how DMA map happens. Device needs to DMA data to and from guest memory. QEMU calls into vfio mdev to register guest memory for DMA operations. In order to do that, QEMU calls mapDMA IOCTL. Then this mapDMA IOCTL is passed further down to muser.ko. muser.ko keeps the track of the physical pages which are behind the guest memory. And then this mapDMA command is passed to user space to libmuser. Then libmuser again calls back into muser.ko to set up the DMA memory. In order to do that, libmuser invokes mmap system call on the muser control device. Then muser.ko inserts the device memory pages into the VMA of device emulation. And once this is done, the control goes back to QEMU. One important thing to note here is that the guest memory pages are being shared with device emulation. In order to achieve this, QEMU must be start with share is equal to yes operation, which enables the guest memory shareable. MUSER also keeps the tracking of GPA to current VMA mapping. So device emulation can always query for this mapping. So let us see how mapping of device memory and register happens. So the PCI regions can be mappable or IO accessible. It totally depends upon the implementation of device emulation. If the PCI device is IO accessible, then the device emulation needs to implement the read and write, which comes on the PCI regions from QEMU side. And if the PCI regions is mappable, then QEMU calls into vfio mdev framework to map the PCI region. To do this, it calls mmap on the vfio device file descriptor, which is the character device itself. Then this mmap is sent further down to muser.ko. Then muser.ko sends this mmap to libmuser. Then libmuser calls back into the device emulation, where device emulation can implement its own logic. And at the end, it should again call back into libmuser by invoking lmmap API, which is exposed by libmuser. Then this lmmap calls into muser.ko in order to set up the device memory. To do this call, it again calls mmap on the control device, which is the character muser device. Then muser.ko allocates pages for the device memory. Then those pages are inserted into the VMA of device emulation as well as into the VMA, which is passed by vfio mdev layer. Once this setup is done, the control goes back to QEMU. So one important thing to notice here is like the device memory pages stays inside the kernel with muser.ko. So even if device emulation crashes, restarts, or some upgrade is needed, it can always connect back to the device memory into the kernel, which is with muser.ko. We also support sparse mmap. If device emulation has interest in using sparse mmap, it can easily use it. So let's see how interrupts are set up. So QEMU passes IRQFD. This is the file descriptor which is used to trigger the interrupts into the guest. Then this IRQFD is passed to muser.ko. muser.ko installs this IRQFD into the file descriptor table of device emulation. By doing this, it is very easy to trigger interrupts into the guest by device emulation just by calling lm-irq-trigger API. Currently, muser supports INTX, MSI, and MSIX interrupt types. So muser framework handles all the vfio and PCI specification related implementation. So this makes writing device emulation very easy. So now Thanos will explain more about the APIs exposed by libmuser, and he will also show us how easy it is to write a device emulation in user space using muser framework.
So what we see here is pretty much it. We have a struct that describes PCI region, whether it's readable, writable, size, a pointer to a function that is called whenever the region is accessed by the guest. The function looks like this. It takes a buffer receiving a data being read or containing data being written, whether it's read or write, a count and an offset. There can be obviously up to 9 such regions. They're all grouped into the reg info array. Unused regions are left blank. In the same struct PCI info, we also declare the absolute bare minimum PCI information we need in order to emulate a device, which is the vendor device ID, class code, etc. We also specify the number of IRQs for each IRQ type our device supports. We can also provide PCI capabilities. We only need to specify the ID, size, and a callback function for the capability. The content of the capability itself is maintained by the device emulation. All this information is grouped into a single struct, device info, which is passed to function context create, which creates an muser context. This context is then passed to function context drive, which effectively realizes device emulation. From this point, we can start the guest. The framework also provides a function to interrupt the guest, and also a set of functions used to map guest physical addresses into the device emulation's virtual memory space. So here's how a device looks like in the guest. A device emulation looks like. We have the vendor and device ID. We only have, let's say, only one PCI region, bar 0. It's readable, writable. It's 64 bytes in size. And accesses to this bar are handled by the bar 0 callback, which is declared here. And our device also supports in-text interrupt. So the only thing now our device emulation does is simply receive callbacks whenever the guest reads from or writes to this bar. The standard PCI header, which is the first 64 bytes, are completely handled by the MUSER framework. Now, there are many functions MUSER doesn't handle yet, most importantly, live migration. There has been some work. It's not there yet. This is the next big thing we need to tackle. We would also like to make MUSER restartable. The framework architecture supports this, but we haven't yet standardized it as a function. We would also like to make MUSER, libmuser multi-threaded, and also to be able to poll for commands from the kernel rather than having to block. Also, a never-going goal of MUSER is to make implementing a PCI device as easy as possible by handling as much of the complexity as possible from the user. For instance, there is a lot of room for improvement in handling PCI capabilities. We would also like to introduce additional language bindings, not only C. In fact, we have a device emulation implementation in Python in less than 10 lines of code. We would also like to provide more examples, for instance, how IRQs or memory mapping a device can be used. And finally, we would also like to be able to trap memory writes when the device supports memory map. This is important when polling is used because we could temporarily suspend polling in periods of inactivity to save CPU cycles. And now we're going to see an actual device implementation. The device we will show you is a general purpose input-output device. It's essentially a PCI card with an external pin that can be either 1 or 0, and the kernel driver in the guest can read. The kernel driver we used is called GPIO PCI IDIO 16. It's a stock Linux driver. So this is our device implementation. We simply declare the vendor and device ID. We only have one bar. Oh, thanks. Oops. Okay. So we only have one. We don't have a vendor device ID, only one bar, bar 2, which is readable and writable, 256 bytes in size, and callbacks to this bar, access to this bar are handled by the bar 2 callback, which is declared up here. And we also support in-text interrupts. Now, as we said, the MUSER framework entirely handles the PCI config space, so we don't have to declare anything here. So the behavior our device exhibits, which means whenever the guest driver tries to access the pin, is to return 1 or 0. And specifically, we flip between 1 and 0 every 3 times the guest reads the pin. And this is, we can see here, the device emulation running. So it's just the binary we compiled, and we pass the vfio UUID. We want MUSER to tell vfio to create a device. And this is how we run QEMU. There's nothing special about it, apart from its guest RAM being shared and the vfio device being passed. And now in the guest, Let's see our device. There it is. And let's read the pin. So we read it 1, 2, 3 times, we get zeros, then 3 times again we get ones, and 3 more times 0, and 1 again, and so on. So this is it. We also have a similar device implementation in Python, except that instead of providing automatically the pin value, we read it from the keyboard. So thank you very much for your interest in MUSER. Please go ahead and play with it. Any questions?
So I actually have 2 questions. First, what's the real use case of this, other than you changing from the kernel space to the user space? And there's no real device to support, so you don't actually really have any real DMA or interrupts going. So it's just all software, right? So what's the real use case here?
Well, if your physical device does not support SRIV, that's one use case, or if you want to have a very complicated data path.
Right, but if you can do that with today's mdev framework already, right?
Well, to do this with mdev framework, you need a physical device.
Right, but
and
you just
in our case, we might not need a physical device. We just need a very complicated data path which talks to other processes or other components in other virtual machines, etc. So we might not even know what the rest of the data path is.
Okay, so my understanding is basically more like a shared memory thing. It's not like a device.
We have use cases. Like, for instance, we would like to implement a virtual NVMe controller that uses SPDK and polling, which with QEMU now, this cannot be done.
Okay. Second question is, how do you plan to support multiple devices inside this libmuser?
Well, each device passed to the, you mean virtual devices?
Yeah, virtual device.
So each device passed to a guest is represented by a control character device.
Let's
so
say
there can be as many such character devices. So your process, the way you implement it, can poll or wait for commands from multiple devices. That's fairly trivial to do.
So one libmuser instance will represent one virtual device? Or multiple?
No, you can use multiple.
Actually, it is not necessary. The device emulation application can show to, by using libmuser, multiple devices. And from single application, you can handle multiple devices. So you can also poll to multiple virtual machines to receive the I/O. And then you can also poll for the completion for the physical devices.
I think I'm not clear my question. The question is, within one VM, right? If you want to emulate multiple virtual devices, can you support that?
Okay. Yes, yeah. Yeah, so for each virtual device, there would be a mediated device, so which is like the vfio device, and the VM can use that device.
And that is a one single libmuser instance, right?
It is not necessary. Yeah, it can be one or multiple also. It is not necessary.
Depends on the implementation.
Yeah,
you
depends
can
upon
code whatever you, however you want.
Thank you for the talk. I wish that functionality had existed a little bit earlier. Does this work when the emulated system has an I/O menu with the DMA you were describing?
Sorry, I can't hear you very well. Say that again.
Does this work when the emulated system has an I/O menu, the DMAing? Does the addresses get translated?
Oh, yes.
Okay. And the other one, you said it's an advantage that we can have a single process, but can we also have multiple processes so that we have kind of a security boundary between the emulated devices?
Yes, so multiple processes can link to the library and they can be started individually.
Thank you.
Hi, so my question is kind of a follow-up to the previous question about IOMMU. So one thing is translating the addresses, But the other question is actually enforcing that memory protection so that if you have one process that's doing devices for multiple VMs, if this process is compromised, it doesn't have access to the memory, full memory space of all VMs. Instead, it only has access to what was permitted using the IOMMU. Is that something that's available? Is that something that's possible to implement?
No, actually, this is one of the disadvantages because if you share memory, we have to have access to the entire guest's memory in order to DMA. So.
Yes, but you do have the MUSER kernel module, so maybe it would be possible to do something there so that the user space process doesn't get full access to all guest RAM all the time. I guess that's the direction I'm wondering if it's possible.
It's going to be very expensive. So our use case is high performance. So our translation is generally just a linear translation of memory address. If we want to support that, there will be a cost and it won't perform as well. But apparently it might be possible to do, of course.
Hi, great talk, by the way. So I have a question regarding the ability to upgrade the user space process while the VM is still running. So because mdev usually mediates the slow path, the control plane, then theoretically, after, for example, the rings were set up and the fast path was already set up, I would like, for example, for the next VMs or on the next reboot of the VMs, if there is a bug there, to be able to upgrade that user space process. And most of the time, because the VM has already booted and set up the data path, then I don't care if I will be able to replace that user space process. So it won't disturb the fast path, right? Because the resources will still be not mediated. So do you plan to add some ability to upgrade that user space process for maintainability?
You mean the user space process that provides the emulation?
Yeah, because it emulates only the slow path. I want to do that without the need to take down the VM, so that on the next reboot it will work with the working version.
I suppose that's like easily doable.
Yes, it's easily doable because the device memory pages are inside the kernel, and when the process restarted, it can always connect back to the device memory.
Yeah, so
discard the old process and pick up the new one if the VM restarts. Yes, of course.
So it will reconnect to the mdev user kernel module driver. Yeah, so I think that is important. Just okay.
I think the question back here regarding the IOMMU was a vIOMMU, in which case you do not have the entire guest memory mapped through vfio. The vfio DMA map is the IOVA address relative to the device. So does it actually work with a vIOMMU? Not yet, okay.
Bit connected to what some people asked previously. So there seems to be an obvious overlap here with the multiprocess project. So have you talked to these guys?
Try to look into it. I'm not aware of how well this is progressing, etc. But I think it definitely matches this disaggregated model, which gives us the benefit of being able to upgrade or be more resilient against failures.
Okay, thank you.